Okay, so we were talking previously about a family of Poncelet triangles, these blue triangles here, inscribed in a circle and circumscribing a concentric inellipse. And we were also associating with this family an inparabola constructed, so here's the inparabola, constructed by specifying its focus, which must lie on the circumcircle. And this is true for any triangle, right? The foci of all possible inparabolas for a fixed triangle lie on the circumcircle. So if I move my focus around, I'm sliding it over the circumcircle, I get a different inparabola. So this is scan number 1, and I can also scan Poncelet triangles by keeping f constant, and in that case I get a different inparabola. And I'm showing here the vertex of this inparabola and the projection of f on the directrix. What we saw in the previous video was a very curious fact, and that had to do with the fact that, let me move f a little bit to the side here, maybe here. It was the fact that over Poncelet, the vertex of this family of inparabolas with fixed focus describes a circle, sweeps this green circle. Okay, and furthermore, the circle contains a focus itself and is tangent to the caustic. So I'm actually showing the center of this green circle here by this green dot and the point of tangency with the caustic. If I move the position of the focus to a different spot on the circumcircle, that locus remains tangent to the inellipse, right? Okay, and furthermore, and this is actually a simple corollary, the locus of the projection of the focus on the directrix, the projection of the focus through the vertex onto the directrix, this point C here, this directrix, the locus of C is a twice-sized circle respective to the locus of the vertex, right? So you can see that. Let me actually move this focus to a non-symmetric position. So here's the focus, the fixed focus. Here's the inparabola. Here's the locus of the vertex. So the vertex is currently here. V is currently here. It's in a particular spot on its locus. So you can just first of all watch V as we traverse Poncelet. And because the point C, which is a projection of F on the directrix, is basically at twice the distance that V is from F, you're going to be sweeping also a circle which also passes through F. And now the center of the circle is a point of tangency itself. It's this orange dot over here. Now here's a couple of new results or new observations. The envelope of my directrices, okay, is a fixed point. It's this point W, which is actually diametrically opposite to F on the locus of its projection onto the directrix. So here's the locus of the projection on the directrix. Here's a diametrically opposite point, and I'm calling this W. Now watch how the directrix is actually rigidly rotating about W. It doesn't matter where my focus is. I'm going to just place the focus over here. You can see that W continues to be stationary. You can see here that the focus, the center of the vertex locus, the point of tangency, and W are all obviously collinear along this diameter. So this is new observation number 1. Now, some of these observations have been made in parallel with Professor Liliana George, so I just want to make sure to mention that. She's been working independently and saw the previous video and sent me some observations, so I don't know which ones of these she made independently or not. Another very curious fact, which actually I know this one specifically Liliana told me about, is that over F, right, you can see here that if I vary my F, the center of, obviously, the orange locus is going to be the caustic itself, because that center is always on the caustic, but the locus of the center of my vertex foci is an ellipse. So as I jog, not Poncelet, so imagine that I'm actually doing a complete revolution of Poncelet to sweep this green locus, but now if I sweep the focus itself, you will see that the center of the locus is sweeping an ellipse. And this ellipse is concentric and axis aligned with the caustic. So this is a pretty nice harmony over here, right? You can see that it's not confocal. I can see the foci of this green ellipse are shown here. And it's not homothetic either, okay? And how do I know it's not homothetic? I'm showing here that the caustic has an aspect ratio of 3.2. The locus of the sweep of the projection of the focus on the directrix is the caustic itself, so it has the same aspect ratio. But the aspect ratio of this dash green locus of the center of the focus locus has a different aspect ratio, and it doesn't seem to be trivially related by some integer rational factor here, okay, between these two. Okay, so it's a nice result nonetheless that the locus of the center of the focus locus is an ellipse. Now, one thing I haven't done and is actually to see what the locus of this fixed point W, and it's fixed over Poncelet, right? What is the locus of this fixed point W? It looks like it could be something interesting as well. If you just follow it visually, it might be actually describing an ellipse as well over all foci. Perhaps it's doing something even more harmonic, like a circle. That would be rather nice. I'm going to leave this as an exercise for those who are watching the video. Let's see if it has any chance of actually being a circle. It could be, right? So I'm actually focusing on the turning point of the directrix when the focus is stationary, and I'm looking at what this thing is doing. Okay, so this is part one. I want to show you guys a couple of other harmonies that come from this construction. I would say this is a pretty amazing first example, because not only is the locus of the focus a circle, but it's tangent to the inellipse. Let's switch now to bicentric triangles, or the poristic family, and let's see what happens. So before I do this, I'm going to have to bring this down so this doesn't explode. Let's make this be 1.05, which is a pretty nice setting. Okay, now look at what's happening here. Again, so actually let's clean this up a bit. What else can I clean up? No, I have to keep this in. And yeah, so let's just recap what this is. This is a n equals 3 family of bicentric polygons, right? So the poristic family. I'm keeping f stationary over here as before. I can place f somewhere on the circumcircle, and I can watch what's happening to the inparabola as I jog Poncelet, right? So as I light up the associated objects, you're going to notice that, again, the locus of the vertex is still a circle. The locus of the projection of the vertex on the directrix is the orange circle. And we still have the same phenomenon, that point W, which is simply the reflection of F on the center of the orange locus, okay, so diametrically opposite to F on this orange locus. This is still the center of rotation of my directrices as I traverse Poncelet. So that point W is still obeying the same kind of construction rule. Doesn't matter where F is. I can place F on the bottom here of the circle. Everything is sort of vertically symmetric. So let's place it over here, for example, or actually close to this location over here. And let's see what happens. Let's put it over here to make these guys rather small. And let's jog Poncelet. And you can see that we got the same phenomenon. W is diametrically opposite to F on the orange locus. Okay. Now, what are the loci of the centers of the loci? So we got a pretty nice harmony here on the bicentric family. The locus of the center of the vertex locus So let's animate that over the foci so you can see what I mean. Just watch what the center of this green locus is doing. It's actually sweeping an ellipse. How do I know this is an ellipse? Because it's being numerically fitted by these squares, and I can see the foci of the ellipse here. Here's one focus, here's another focus. There's nothing really harmonic about this other than the fact that it is axis, so its minor axis is along the OI line. So here's the circumcenter of the family, this black dot, right? Here's the, and you cannot see it here, but if I'm just going to talk about this in a second. Here's the incenter of the family, and you can see here that the center of this dash green locus of the center of the locus of the vertex, that center there seems to be the midpoint between the circumcenter and the incenter. Furthermore, the locus of the projection of the focus on the directrix, now no longer coinciding with the caustic, okay, is internally tangent to the caustic. This brown circle here is tangent to this also elliptic locus, and its center is the incenter. Okay, now let's check what's going on with the axes of these two guys to see if there's anything harmonic or harmonious. Yeah, you could maybe say this is 2/3, and we should try to understand, this looks like it's 0.666, there's some numeric approximations, but I'm not sure. This could be 2/3, the aspect ratio could be 2/3 of the directrix, but I would be surprised if this is the case. Let's see here. No, it's not, right? I just changed a little bit the parameters of my bicentric, and you can see that I'm getting different numbers here. So this is nothing special. We just have to use some analytic geometry here to actually figure out what's going on. Okay, if I vary my bicentric family, I can see that, yeah, these loci can intersect. So this one is not necessarily interior to that one, but its center is always on the incenter, and both ellipses are axes aligned with the OI, so their minor axes are the OI line. The center of the dash green seems to be the midpoint of the incenter and the circumcenter of the family. Okay, so this is very pleasing, and I'm going to finish with a surprise. You can see here that point W is still stationary, diametrically opposite to the focus with respect to the center of the solid green focus. Okay, now let's finish with a surprise here. It's not much of a surprise, but it's kind of a neat phenomenon. So let me turn everything off. Yes, I want to introduce another family, which is actually the family of excentral triangles to the bicentrics, but let's forget about the bicentrics, and I'm just going to define this family as being, let's rotate Poncelet here, family of Poncelet triangles. Okay, let's put the Inparabola above it. To do this, I have to place the focus up there. Okay, so the focus is over here. This is a family, as a Poncelet family of triangles, inscribed in a circle and circumscribing an ellipse where one of the foci of this ellipse coincides with the circumcenter. So you can see here that this is my caustic, and one of its foci, here's the center of the caustic, one of its foci coincides with the center of the circumellipse. Right off the bat, you see that there's some magic going on here. The directrix, this could be a coincidence, right, is passing through the other focus. What if I rotate Poncelet? Look at what's happening to that directrix. So the envelope of the directrix is the other focus of the caustic. Very strange, right? All right, this is the first thing. Now let's actually draw the locus of the focus and the locus of the projection of the focus on the directrix. So the green, solid green, and solid orange. Right away you notice that since, as we said before, point W is that fixed center of rotation of the directrix, and we just saw visually that the directrix is always going through that other focus, point W is right there, right? So point W is right there as I play around with Poncelet. So this is surprise number one. So we're looking at several families that are inscribed in a circumcircle. Perhaps a conjecture that we could make here is that for any Poncelet triangle family inscribed in a circle, regardless of the caustic, and I haven't tested a whole lot of other examples here, but we've seen 3 or 4, regardless of the caustic, the locus of the imparabola vertex is always going to be a circle. But let me finish with now the trajectories as we sweep F, right? As I sweep F, I want to now study the trajectories or the loci of the center of the vertex locus and the center of the focus projection locus on the directrix. So the centers of the green circles and of the orange circles. Let's go ahead and draw those. So something very cool happens here. Both loci are circles. Okay? And the locus of this center here is a circle, this dashed green circle, centered on the midpoint. Let's see if this is really true. I don't want to claim something is true when it is not. It looks pretty, yeah, it looks true. Yeah, so I've made this caustic be a bit more eccentric. So visually speaking, it looks like this center green here of the dash green circular locus is the midpoint between the center of the caustic and one of the foci, which is the circumcenter of the family. Okay, the other locus is also a circle, so let's bring this back to where we were before, something like that. I want to avoid, yeah, there we go. So the other locus is also a circle, so now we have 2 circles. And I want to jog the focus. And ignore those flashing axes. They are circles. It just means that I'm close to being an ellipse, but they're numerically unstable there, but they're 2 circles. And again, I could do the same, ask the same question. If I stop this guy here, and I move Poncelet, what is my point W doing? Nothing, right? In this specific case, and only in this case, is W stationary. Is that what I did? Yeah, I did this. Is W stationary over all foci? So this is very special, right? Point W is stationary over all foci positions. If you go back to the bicentric case, you're going to see that that was not the case. Let's put it like that. Say 105. Here's the bicentric family. Here, as I jog my focus, point W is moving. What is that locus? Is that locus an interesting curve? Is it a circle? Is it an ellipse? It looks interesting. So I'll leave this as an exercise. And just to sort of give you guys one more example where we have a Poncelet family inscribed in a circle where these 2 loci, both of the vertex and its projection on the directrix, are also circles. I'm just going to go finish with a 4th example, a Brocard family, but so that this thing doesn't blow up, I have to place this guy in 2. Okay, it already blew up. It's fine. I'm going to try to come back alive here. Yeah, 2.5 maybe. Yeah, there you go. Let's go 3. Okay, so this is the Brocard family. The Brocard family is inscribed in a circle and circumscribes a Brocardian ellipse. The foci of the inellipse are the fixed Brocard points of the family. So what do you get here? Again, we get that. Let's place the focus in an interesting place. Place it over here. And let's jog this family a little bit. So we get that the locus of both my inparabola focus and the projection of the focus on the directrix, they are both circles. You have a fixed point W as I jog Poncelet at the diametrically opposite thing. So this is giving a bit more credence to the conjecture that any Poncelet family inscribed in a circle will have this phenomenon of circular locus of inparabola vertex and a fixed point W, which is the envelope of the directrices. Now, what you get here now in terms of jogging F, right? Let's stop Poncelet and let's jog F, and let's show the locus of the centers. Again, you get, and this is the Brocard family, you get 2 ellipses for the loci. The dash green ellipse of the center of the green circles is aligned with the inellipse, axis aligned with the ellipse. Its center seemingly is the midpoint of the inellipse center and the circumcenter, so here's its center. And the locus of the center of my orange circles is, again, like in the bicentric case, externally tangent to the caustic, and its center coincides with the center of the Brocard inellipse. So I can jog Poncelet and watch W not move, or I can jog the focus and watch W move. Again, we can ask the question, what's the locus of W as we traverse F? Okay guys, see you in the next video. Hope you've enjoyed this one.